we want to prove that A minus B is a subset of A. How do we prove it? Maybe somebody else wants to help me.
If no one else wants to do it, can I try?
All right, yeah, sure. So we want to prove that A minus B is a subset of A. Suppose what?
Is it suppose A and B are any sets?
Yes, suppose A and B are any sets. And
then suppose X is any element of A.
Suppose X is any element of what?
A minus B.
We want to start with the left-hand side.
Is any element of A minus B?
Yes, any element of A minus B.
Then
what?
By definition of...
Let me start indeed. By definition of what?
Is it going to be the definition of intersection?
Do we have here intersection on the left?
No, it's not.
Is any element of A minus B. So here by definition of...
Oh, then X is in A.
Yes.
And X is in A minus B by...
Well, let us go back to definition of the difference. B minus A means the set of all elements that are in B but not in A. Here, instead of B minus A, we have A minus B. So what do we do?
My trouble right now is that I know if it's in A, then subtracting whatever else from it means that whatever's left over is still in A.
Yes.
Meaning that that's true. I just don't know how to word that correctly, mathematically speaking.
So let us go back. Here, B minus A means all elements that are in B and not in A.
Oh, okay.
Here we have A minus B. So then what?
Then X is in A and X is not in B. Right?
Exactly. X is in A and not in B by definition of
difference.
So
A minus B is in A?
No. So X is in A.
X is in A, yeah.
So X is in A. Guys, any questions here?
Sorry, is A minus B is also a subset of B in that case? Or does that not work?
B? No. Please take a look at this. Here is set difference, B minus A. Note that B minus A is a subset of B, but not a subset of A. Same as here, A minus B is a subset of A, not a subset of B.
Okay. And will we need to know that specific property A minus B is a subset of A, or we just need to know how to prove it?
Well, here we use these rules in order to illustrate element method of proof.
Oh, okay, yeah. I got you.
For example, so far we discussed properties that are not from the list. However, this one is number 3, distributive law. Do you want to do it together?
Yeah, I can try to work on that.
Okay, Jimin, so here let us try to prove this. So this is one of the distributive laws. This law is over here. It's 3b. So let us do it together. Suppose what?
A, B, C, and R sets are any sets.
Suppose A, B, and C are any sets. Note that in order to prove that this is equal to this, we have to prove that the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. Why? by definition A is equal to B if and only if A is a subset of B and B is a subset of A. Correct? So, step one, let us prove that the left-hand side is a subset of the right-hand side. Let X be some element from the left-hand side. By definition of intersection, so Jimin, what do we put here?
X is in A or X is in B union C.
Not or, X
And.
is in A and X is from B union C, correct? Thus, X is from A, and by definition of union, X is from B or what?
X is in C.
X is from C. So once again, over here we put X is from A. Over here we put X is from B union C. Therefore, obviously, X from A. And by definition of union, X also from B or X is from C. Next, so once again, X is from A. And then we have X's from either B or C. Let us consider these two cases. Suppose X is from A and X is from B. Then we will consider the case X is from A and X is from C. So once again, case one, X is from A and X is from B. In this case, by definition of intersection, Jimin, what do we put here?
X is in the intersection of A and B.
X is from intersection A and B. And so by definition of union, X is from A intersection B or X is from A intersection C. And we're done. Now, case two. In this case, by definition of intersection, so what do we put here? X is from?
Intersection A and C.
A intersection C. And so by definition of union, X is from?
You just copy the last thing from the case one.
We just copy same thing. So in either case, X is from here. We are done. Part one is done. Now, part two. Now we want to prove that the right-hand side is a subset of the left-hand side. It's exactly what is written here. So suppose X is any element from the left-hand side. It's written. By definition of union, Jimin, what do we put here and here?
The first would be A intersect B. The second one
A
would be
intersection B. The second part will be?
A intersect C.
A intersection C. So, since here we have or, we consider two cases. Suppose X is from A intersection B. In this case, by definition of intersection, what do we put here and here?
X is in A and X is in B.
Absolutely, X is in A and X is in B. Since X is in B, by definition of union, X is from B union C. Therefore, we just said X is from A, we got X is from B union C, so X is from A and X is from B union C. Therefore, by definition of intersection, what do we put here?
The right-hand side of what you want to
Exactly.
prove.
X is from A, intersection B union C. Now, case two. Suppose X is from A, intersection C. In this case, by definition of intersection, what do we put here?
X in A and X in C.
X is in A and X is in C. So since what?
A, so Since X is in C, by definition of union, X is in B union
Since
C.
X is in C, by definition of union, X is
In B union C.
in B union C. So over here we put same thing, but here instead of X is in B, X is in C. Then hence, what do we put here?
You just copy the entire
Just
thing.
copy,
like,
absolutely.
From the case one.
Hence, X is from A and X is from B union C. And so by definition of intersection, X is from this. And we are completely done. Folks, any questions here?
Can you go over the number I, the one before again?
Over here.
Yeah. Yes.
So yes, absolutely. We want to prove that the left-hand side is a subset of the right-hand side. So pick any element from the left-hand side. The left-hand side is intersection. So by definition of intersection, X is from A. So here we put X is from A and X is from B union C.
Okay.
Conclusion, X is from A by this. But then remember once again, over here we have union, B union C. So by definition of union, X is from B or X is from C.
So why did you put X is in A before?
Oh,
Thus X is
here
in.
X is in A.
Let's see.
X is from
Oh,
intersection,
okay.
X is in A.
Okay.
Thus X is in A.
Okay.
But here we have two possibilities, X is in B or X is in C.
Okay.
Therefore, case one, X is in A and X is in B. Case two, X is in A and X is in C. And the result follows.
Okay, and then so the thing you just said, so X is in A and X is in B, is that the definition of intersection?
Well, exactly.
Or that's the definition of union.
So once again, the way how we jump here, if your question is how we jump here, it's
Oh no, I understand that. I'm just asking. So I thought or was union and was intersection. Is that right?
or is union and is intersection. Yes.
So in the definition of union, so is that thing in parentheses? Is that the definition of intersection?
This is intersection. Just because of that, it's written intersection.
Oh, and
X is in A and X is in B. Therefore, X is in A intersection B.
well, no. So that's by definition of intersection. I'm asking in parentheses.
Yeah.
X is in A and X is in B. Close parentheses. What is that the definition of? What definition is that?
Yeah.
Or is it?
No, I just explained what is case one. Case one means X is in A and X is in B.
Okay.
I
Okay.
just
Then
explain what do we mean by case one?
Okay.
I mean this.
Right. And for
This because X is always from A,
okay.
and here we have a choice. X is from B or X is from C. Suppose X is from B. Then we have the following: X is from A, which is over here, and X is from B, which is over here. Does this make sense?
Yes. And then if you were doing it for the opposite, where it's A union B first, is it a different proof? You couldn't do the same thing. You'd have to do something.
There is no way we can use here union because we have and.
Right. So there's another way to do it then. Okay. Okay. That's fine. Okay. Thank you.
Sure. Other questions?
I have a question.
Yes, John.
Do we necessarily have to break it up into the two cases, or can we just say, because X is either an element of B or an element of C, therefore it must either be an element of A intersection B or A intersection C?
I would say it's not that simple to combine these two cases in one case, because the right-hand side is a little bit complicated. The best way to handle this situation is to split into cases.
Could you say that last statement one is just an example of De Morgan's law, since it's X is a member of A and X is a member of B?
Give me a second. We cannot use laws yet. Here we do everything by definition. On the next slide, we will use laws. Here we are trying to prove laws.
Asking because De Morgan's law is from logic, so I didn't know if that was allowed or not.
No, well, later we'll show you connection between set laws and logic laws, but we cannot do it now. We cannot use this. No, not yet.
All right, cool.
Can I ask a question again? So in case one, you put at the end of it by definition of union, the definition. Yes. How can you do that before case two, showing that A intersection?
Very good question. Once again, over here, we put X is from A intersection B. Over here, X is from A intersection B, correct?
Yeah.
Since X is from A intersection B, it is either from A intersection B or A intersection C.
But we haven't done case two yet. So A saying that
No. We don't need it. We don't need it. We already know that X is from this.
Right.
Therefore, X is from this. Because union means or.
But the A intersection C hasn't happened yet. How do you know that?
It does not matter for us. Once it does not matter. We can put here whatever. Since X is from this, X is from this union whatever.
Okay. And then when you say case one and case two, are you saying either case one or case two, and that's why you can say or? That's why you...
Here, once again, here we have or. So we don't know yet, X is from B or X is from C.
Right, so the reason you can put a union in between at the very end of the proof is because case one or case two is an or situation. It's not
No. So bear with me. By this portion, we conclude that X is from A intersection B, correct?
Oh, right.
Now, since X is from A intersection B, X is from A intersection B union, or whatever. We don't have to put here A intersection C. We can put here whatever, any set.
Okay.
You see it?
Right, and then so at the end of the proof, you say, let's see, you say hence in either case, X is in A and B, A.
Well, since in case one, we conclude this, and in case two, we conclude absolutely same thing.
Right, so in that case, you're saying or. You're saying case one or case two.
Yes.
Okay, gotcha.
Mm-hmm. Other questions? Okay, guys. Now, in this way, we can prove all these laws. So as an illustration, we proved 3b. But using this approach, we can prove any of these laws. Now we can use these laws in order to prove more complicated set identities. Let me put two slides together. So please take a look at, okay, let us click on this, click on this, click on this, and 6.3. So here we have several examples. How do we prove, for example, number one? Once again, one way to prove it is to use the element method of proof. but it will take long. Instead, let us use set identities. So please take a look at this. A minus B union A intersection B. By law number 12, we can rewrite the difference as the intersection. So by law number 12, A minus B is A intersection BC. Then we use law number 3, distributive law. But be careful, we use law number 3 reading from the right to the left. Observe that A is over here and A is over here. By 3B, we can factor it out. So we have A intersection B complement union B. Then, and again, be careful, it's a common mistake. Often students use complement law immediately. No, we can't. First, we have to use commutativity, because in complement laws, we don't start with A complement, we start with A. So first, we switch positions, and then by 5A, B union BC is the universal set. Lastly, by law 4B, A intersection U is A. And we are completely done. Any questions here?
I was wondering, the first one is we have A minus B union A intersection B is equal to A. Where does the right?
How we get this? It's law number 12. It's law number 12. A minus B is A intersection BC.
Oh, that makes sense. Okay.
A minus B is A intersection BC. Law number 12.
Yes, thank you.
Other questions?
In step 3, why do we have to do B union BC? Why can't we just do?
Yes. Very good question. Because law number 5 does not start from A complement. It starts from A.
But it's the same thing, right? One half.
Well, it's same thing by law number 1, by commutativity.
Oh, okay.
Does this make sense?
Yes.
Other questions?
We applied law 1 in the first step, like instead of going from 12 to 3, went from 12 and then applied 1 and then 3.
Yes, absolutely. We can switch positions first. We can do A intersection B union, A intersection BC. And then we factor out A. And then in parentheses here, we'll get B union BC. Absolutely. So this is not the only way to prove it. Okay, guys, next, how do we prove this? Now, once again, you can say, hey, wait a second, it's basically number 3. No, guys, it's not number 3. Because in number 3, distributive laws, we do not start with parentheses. We start with A. So step 1, apply commutativity. Put C first. Then we apply distribution law. C intersection A union C intersection B. And lastly, commutativity again. We switch positions over here and positions over here. Done. So problem number 2 is a wonderful example of commutativity. We use here commutativity actually 3 times. 1 time here and 2 times here. To jump from here to here and to jump from here to here. Number 3, how do we prove this? Well, we start with 12. We replace C minus A by C intersection A complement. Then we use 12 again in order to rewrite this difference as A union B intersection C intersection A complement and the whole thing complement. Then we use one of the De Morgan's laws. So we use De Morgan's law in order to expand parentheses here. We get C complement and then we replace intersection by union A double complement. Then we use double complement law in order to rewrite A complement complement as A. Then we use commutativity to switch positions. Lastly, we factor out A by distribution and replace this by B minus C by law 12. Number 4, nice example. So here we have A minus B minus C. If you try to expand parentheses, you will get a nonsense. We cannot just expand parentheses and get A minus 2B plus C. Set identities don't work this way. So instead, we use law number 12 in order to replace A minus B by intersection and B minus C by intersection. Then we use law number 12 again to replace this difference by intersection. And of course, here we put complement. Then be careful. For the first time, we use 2 associativity. By 2, we can rewrite what is written here as A intersection of what is left. And what is left will be BC intersection, B intersection complement of C, the whole thing complement. And then by 9, and remember 9 is De Morgan's law, we can put C around the whole thing. And of course, we replace intersection by union. And now, absorption law. If we have B union, and then in parentheses, B, again, intersection or whatever, the whole thing becomes just B. And of course, we add complement. And lastly, what is written here is A minus B.
I'm confused about the third line to the fourth line, how the De Morgan's law worked.
From here to here, yes.
Yeah.
So let us read De Morgan's law backwards. So we have set number 1, union, set number 2. By De Morgan's law, instead of B, we have B complement. Instead of this, we have same thing, complement, and then instead of union, we have intersection. Does this make sense?
Yeah, yeah.
Mm-hmm.
So
yeah.
So if you were not to go backwards, instead go from the third line to the fourth line, are you just taking a complement, like a double complement and canceling it out or something?
Well, look, we can use De Morgan's law reading from the left to the right, or reading from the right to the left. So we are fine going from here to here. We just, what we do, we just use 9A, reading from the right to the left.
So you took the C out and flipped the, you took both C's out, put it on the outside.
We think about this as about A, and we think about this as about B.
Okay.
Does this make sense?
Oh, okay. And then from the changing to A intersection B to the C. But what rule was that? What rule was that?
Say it again for how we go
From line 4 to 5. Yeah. What rule is
from
that?
here. Yes, this is absorption law.
Oh, okay. Okay.
So if you think this is 10A, if you think about this as about A and C complement as about B, the whole thing becomes this.
Do you mind for me going back up to case 2 from the last page and just telling me what they were again? I'm just trying to double check.
The element method?
Yeah, just all the lines from case 2, part 2, case 2. Yeah,
Part 2, case 2, yes, absolutely. So once again, we start from the left-hand side. Suppose X is some element from the left-hand side. By definition of union, X is from this or from this. So case 2, suppose X is from here. It's exactly what is written here, right?
Right, I'm just trying to check what goes in the blanks.
Or in the
yeah.
blanks.
Right.
So in this case, by definition of intersection,
Right.
X is from A and
then X is in C, yeah. Okay, and then
Right.
after that I can.
And then since X is from C,
Okay.
by definition of union, X will be from B union C. So here, over here, we put same as this.
Oh, okay, same. Okay. So let's see. Then you can just say hence X in A and then X in B and C.
Hence, and then we copy same thing.
Okay.
And then by definition of intersection, X will be from A intersection B union C.
Okay, got it. Thank you.
Other questions?
Yes, actually, for rule number 12.
Yes. Yes.
Ron, let me. I have a picture, John. Let me share my video real quick.
Well, actually, let me show you the picture. Here, please take a look at set difference. B minus A. It's a little bit confusing because here A minus B.
Yeah.
But for B minus A, it will be B intersection A complement. Correct?
Yeah, my bad. For some reason I was seeing as A union, and I was confused because I figured there were points in U that weren't in A.
No, it's
yeah,
intersection.
Okay. Yes,
it's intersection.
Okay, yeah, that makes sense.
Mm-hmm. Once again, if here you consider, once again, in our case, in this case, should be B union A complement. So A complement will be everything outside A, correct?
Yes.
And if you consider everything outside A, intersection B, we'll get exactly what is written here.